about the glitches there. I'm Tom Dimiduk. I work at Harvard doing digital holographic microscopy. We've spent the past number of years building up some tools to work with holography in Python. So I'm guessing most of you have seen holograms, maybe in Star Wars or on your credit card. That's a little bit different than what we actually work with for doing science. So we end up using holograms to study microscopic particles, sort of micron diameter, often sort of plastic or silica particles, studying motion, approach to interfaces, cluster dynamics, things of this sort. So we like holography because it gives you very simple imaging. You just need a laser, a lens, and a camera, and you can get three-dimensional imaging out of this. You can do this because you move the processing, all of the smarts, into software. A hologram will come out looking like this, not exactly what you're used to seeing for an image. We can't use traditional image processing algorithms. Instead, we have to go to more physics-based approaches for working with images. So we can do what's the equivalent of what Gabor did with holograms. If you shine light back through a hologram you've recorded and see a three-dimensional image, which is the numerical analog is called reconstruction, which lets you take this image and refocus to something else. Or what we've had more luck with for doing high-precision measurements is doing an inverse light scattering problem and actually fitting a model and then determining where particles are from that sort of model. So this works because holograms, unlike normal images you take, actually record phase information. So you'll have a particle, if we have some particle we're observing, we shine laser light on it, some of it will scatter, and then light that doesn't scatter, those two beams will interfere, giving rise to a pattern of light and dark fringes that encode the phase of the light that came in, which encodes basically the angle it traveled. And so that tells you, you can use that to back out what three-dimensional position an object should have been at in actual space from a single two-dimensional image. This is useful because it means you can take images very fast with simple hardware and still get back three-dimensional images. So we need a little more metadata than you usually use for recording an image. We need pixel spacing, which anybody who's done quantitative imaging is used to. We also need to know the wavelength of the light and the index of refraction of the material you're working in to be able to compute these phase calculations. So our code has stuff for when we load an image, we just automatically associate the relevant metadata with images so that we can do our calculations. So the first thing I was talking about is we can do this numerical refocusing, which is just propagating light by a convolution propagation. So you can take an image we've loaded, tell it some distances we want to propagate to, and see what kind of results see what you'd get. Oh, I'm sorry. Can people over on that side of the room see when I'm coming and pointing? I could use a mouse pointer instead, but I like pointing with my hands. Or the second piece I was talking about, where we do inverse scattering by setting up a model of what's going on. And we have code to make nice clean parameterizations of the physical model you have, and then you can compute a fit to that and get back a result which is now, I had a sphere here, I had a sphere here, they were this big, and that can be very precise measurements of our system. So we do this with, we've got a code that we've released. We're sort of up to a 2.0 release. We need to give another release now because the one we've got is a little bit stale. But we've got this reasonably well documented, available to anybody who's interested in working with holograms or doing light scattering calculations. So we've got sort of an architecture here. If we've got a core piece that does image loading, metadata, basic image math. I suspect we've reinvented a lot of wheels that other people in the community have done, so I'd love to hear from others how you've done these, whether there's cases where we can share code and not have to maintain as much of our own code here. I'm pretty sure Dan, who's speaking next, has some code that we should be using, so we'll be able to cut down our burden a little bit there. And then we've got modules to do the various pieces I was talking about, to do propagation of light by convolution, do light scattering calculations, which are needed to do the fits that are how we actually do our measurements. And then we've got code to do visualizations with MyV and Matplotlib. So these light scattering calculations are, we've got a couple of different scattering theories that use actual physics solutions to Maxwell's equations to compute how light would scatter. The simplest one is based on Mie theory, which is just the solution to Maxwell's equations of spherical object, incoming plane wave, and then what you get coming off. This is useful for spheres that are separated at relatively large distances, or you can use it to work with layered spheres. So some of my research right now is working with lipid membranes, where you've got an object that's like water inside a boundary of fatty acids and then water outside. So we can model that kind of thing. We also have a theory that does an exact multi-sphere superposition to be able to compute all of the near-field scattering, multiple scattering things between a cluster of spheres in close proximity that we can use to model large numbers of spheres. This is actually code that we've borrowed or used from the astronomy community, who use it to compute scattering off of dust particles in space. Turns out it also works great for computing off of particles in water. And then finally, I hooked up discrete dipole approximation. So there's a code to do light scattering off of arbitrarily shaped objects based on discretizing it with an array of points representing the object, and then you can call out from that. This is a big C++ code that's kind of a pain to work with, but we've got a wrapper so that you can give a nice high-level Python interface using all the same tools that we use to work with the other theories and get scattering calculations back from that. Then for our fitting, we've got sort of a pluggable minimizer. For legacy reasons, we have an old, slightly horrific minimizer that does the constraints we need, but it's sandboxed enough that we're, in the near future, going to be moving out to allowing a lot of different minimizers. Can easily parameterize objects for these models. If you take the same objects you'd use to compute scattering, and you can put just a number to tell you I want a constant number, fix this parameter, or you can give it parameter objects telling you to vary this parameter, what guess to start with, and if you need it, you can set limits on the parameters. And then once you've got a model, you just have to tell it what it should use to compute the forward function. So in this case, if I'm working with a hologram, I want to say, use me theory to compute a hologram, and then just one function call to fit the hologram to some data we're working with. And further, there's abilities to go through and model entire time series of using guesses from parameterizations and guesses from one frame to go and work with next frame in a time series. This lets us work with thousands of frames to get movies like that one I showed you earlier. So I had some live visuals. How am I doing on time? Should I pull up my live visualization demos or should I skip them? Okay, I'll keep. So then, last piece we've got is to do serialization. All of our results, we have our objects, some kind of cute code to just take any object and automatically turn it into a YAML text file that represents all of the parameters it has, and then we can load that back in. So this is our save format that's also easily human readable. We're working with things where the calculations we're doing are fairly long, so the cost of serializing to and from text is tiny compared to the calculation times, and it's convenient to have human readable text in case something goes wonky. You can go check and see what's going on. And so we've got some code actually that other people have started to use that you just inherit from a class, and then it will automatically give you this serialization. So if you're interested in doing light scattering or holography, sort of announcing this to this community that we've got a code that should be useful. Definitely want community feedback. We've sort of developed this in isolation and didn't know that much of what other tools people have built, so I'm curious to hear all the places where we've reinvented wheels, could be using outside code instead of working on our own. So thank you.